This presentation will give an overview of the Reconfigurable Array for machine vision inspection, RAMVI for short. This is research conducted at the NSF Engineering Research Center for Reconfigurable Manufacturing Systems in the University of Michigan. The objective of the project is to develop a configurable machine vision inspection system composed of mass-produced consumer hardware components, such as digital cameras and various types of light emitters. These components act as modules that can be assembled into different arrangements fitting the inspection task at hand. This arrangement may allow a decrease in system cost due to the use of standard mass-produced components. Furthermore, since multiple devices are employed, higher performance can be achieved. The concept of element multiplicity to increase system performance was used in the past. In parallel computing, several processors were employed to increase program execution speed, while in redundant arrays of inexpensive disks, RAID, increased performance and increased fault tolerance were achieved through multiplicity of disk drives. The concept of camera multiplicity has been employed in the past for various purposes. Applications include the light-field video camera, high-speed video photography, and seeing through foliage by emulating a synthetic focus. An array with moving cameras was also suggested to improve results. These systems, however, are not oriented towards industrial inspection. The concept of using camera multiplicity to increase the performance of an inspection system is new. To demonstrate the feasibility of this concept, a RAMVI system has been constructed as a testbed system. The system employs several web cameras housed in cells that are attached to each other to create a structure. Lighting elements can also be housed in the cells to create a desirable lighting pattern. The RAMVI software consists of an image acquisition module and of a calibration module that handle the multiple cameras. The entire system is characterized by its reconfigurability. The cameras can be arranged in different configurations. In particular, the system is characterized by its scalability, meaning that additional cameras or other devices can be added to the system. The following example will show how the RAMVI system can be used to increase the resolution of the acquired image, beyond that of a single camera. 5 cameras were assembled together in a row. Each camera was targeted to view a different region of a planar surface. Those regions are displayed in different colors. A partial overlap between the fields of view guaranteed continuous representation of the surface. First, images of the calibration grid are acquired to enable camera calibration. Later, the calibration grid is removed and a part is introduced for inspection by the system. In this example, the combustion phase of an engine cylinder head was inspected. Here are the calibration rig images obtained by each individual camera. Below is a set of images obtained from the engine cylinder head. One may notice the overlapping regions in the leftmost images of the engine cylinder head. Note, however, that simply cascading the images one on top of the other will not result in a valid image, as each image is obtained from a slightly different direction of view and contains a perspective effect. Furthermore, lens distortion contributes to the difficulty of combining individual images. To allow combining the images, each individual image has to undergo 2 procedures. First, the image is rectified for lens distortion. Then, a transformation is calculated that transforms each image to a common reference system. After these transformations are applied, the individual images can be combined to a single higher resolution image. Note that the irregular boundary of the combined image is created due to these transformations. The combined image lacks perspective effect. It shows the image that would have been obtained from a viewing direction perpendicular to the inspected surface. The resolution of each individual image was 640 by 480 pixels. The approximate resolution of the combined image is approximately 1800 by 400 pixels. Thus, by using 5 cameras, image resolution was increased threefold. Note that this increase in performance can also be interpreted as an increase in the field of view while keeping a constant pixel size. The same image and distortion procedures and transformations calculated during calibration can be applied to the images of the inspected part. After applying the transformations, the combined images again construct a higher resolution image. This image can then be processed by commercial software applications to extract accurate dimensional measurements and surface imperfection information. For example, distances between holes can be measured with a relative increase in accuracy. Another example is detection of pores. Note the current image construction method is limited to 2 dimensions. Features not on the calibration plane will not be connected well between camera images. Thus, the constructed image is adequately connected only in the plane of the combustion phase. To effectively use a large number of cameras, an automated calibration technique is required to avoid time-consuming manual calibration. Such a calibration approach based on a color-coded calibration grid was developed and implemented. The following example illustrates its effectiveness. In this example, 18 cameras arranged in no particular order were used to acquire images of the calibration grid. The cameras covered different partially overlapping areas of the calibration grid. The automatic calibration method was able to rectify the images and assemble them in a correct order. This is demonstrated by overlaying the reconstructed image over the original image of the calibration grid. Following the calibration of the 18 cameras, images of the surface of the engine cylinder head were acquired and assembled into a single image. Highlighted areas are magnified below. These areas show image areas assembled from 4 images on the left, 2 images in the middle, and 3 images on the right. Again, features on the calibration plane are stitched properly. Additional information on the RAMVI system and its calibration method is available in these sources. This research is supported by the National Science Foundation. Special thanks to the development team. Thank you for your interest in this brief overview.